0. Now, just before you go into your own calculations, I'm going to go through a sample calculation for you, just to help you with the various different bits that they're going to ask you in terms of working out eventually a ratio or a relationship between the sodium carbonate and the water of crystallization. Okay, so let's just read this question here. This is a question that came up about 5 or 6 years ago in the Leaving Cert. A batch of washing soda crystals, which are hydrated sodium carbonate, Na₂CO₃.xH₂O, had lost some of its water of crystallization by a process called efflorescence. Now, that word efflorescence simply means losing moisture naturally to the environment. It's another way to say drying out. Okay, a chemist was required to determine the percentage water of crystallization to crystals and the value of X, the average number of water of molecules in the formula. Now, just before I read on, see that formula there, Na₂CO₃xH₂O. What that means is that the washing soda we're using has a partial reactant and a partial non-reactant. So what I mean by that is that all the crystals that you use, not all of those crystals will be the active ingredient. Only a part of those crystals will be an active ingredient. Okay, so if I weigh out, for example, as they say here, if I weigh out 2.5 grams, not all of that 2.5 grams is going to be sodium carbonate. Only a certain amount of it is. The rest will be water. So our job, basically in this experiment, is to try and figure out how much of that 2.5 grams is the active sodium carbonate and how much of it is water. And then by means of using the empirical formula that we had in chapter 2 or chapter 3, we're going to try and get a ratio built up between the active sodium carbonate and the surrounding water of crystallization. So let's read the second paragraph. A sample of the crystals were accurately weighed and found to have a mass of 2.5 grams. The sample was dissolved in deionized water and made up to 250 centimeters cubed of solution. Now, 2.5 grams in 250 centimeters cubed. At this stage, we know that as chemists, we don't talk about quarter litres, we don't talk about half litres, we don't talk about 3/4 of a litre. What we do is we say, okay, I'm putting 2.5 grams into 250 so that I'm not wasteful with solution. But in a normal situation, because the litre is the standard unit of volume, that would be the same as 10 grams in 1 litre. Okay, now we're going to come back to that 10 grams in a litre and that 2.5 grams in 250 at the end of this particular calculation. Let's read on. A number of 25 centimeter cube portions of this solution. What solution? The crystals solution. So now we're starting to see 25 centimeters cubed of the washing soda solution were titrated with a previously standardized 0.1 molar hydrochloric acid. The mean volume of the hydrochloric acid was 21.6 centimeters cubed. Now look, they give you the balanced equation as they always will. So the very first thing you do is you write down the two species that you are titrating, the HCl against the Na₂CO₃. And underneath both, you simply write down everything that applies to those two. So let's read that paragraph again. 25 centimeters cubed of this solution. Now that's the crystals made up into solution. So 25 of the washing soda were titrated with a previously standardized 0.1 molar hydrochloric acid solution. So over here you've got your V1 and your M1. Now we know the hydrochloric acid is 0.1 molar. We know that the volume, V2, of the sodium carbonate is 25 centimeters cubed. We are trying to find the molarity of the washing soda. So all I need now is an average titer for the HCl. The mean volume of the hydrochloric acid solution was 21.6. Okay, so now I've got everything I need to work out the number of moles of both. Okay, I've got all the figures I need because we already know that V1 by M1 is going to give me the number of moles and V2 by M2 is going to give me the number of moles on the right hand side. So V1 by M1, I should say, will give me the number of moles of HCl, and then V2 M2 would give me the number of moles of Na₂CO₃. However, look at the balanced equation. The ratio is 2:1, so I have to bring in the N1 and the N2 as the coefficients of both of those substances. Okay, they don't react in a ratio of 1:1, they react in the ratio of 2:1. So what that does is it sets me up nicely with my V1M1. So V1M1 over 2 is equal to V2M2 over 1. And all I've got to do then is fill in the formula, fill in the values. So 21.6 times 0.1 over 2 is equal to 25 times x over 1. And I told you what to do to get x on its own. Bring the 25 down here. So that's going to give you 21.6 times 0.1 all over 2 times 25, and that's equal to x. So now you go to your trusty calculator, you turn on your fraction, you put your 21.6 times 0.1 on the top, and you put your 50 on the bottom, and lo and behold, it tells you in decimal form that x is equal to 0.0432 moles per litre. Because don't forget, the result of titration is always in moles per litre. So as soon as you work out the concentration of the species that you're working with, whose concentration you don't know, as soon as you work out that concentration, it's always in moles per litre. Now, what does the question ask me to do? From the mean volume, calculate the concentration of sodium carbonate in the original solution in moles per litre. Well, there it is. There's your moles per litre. That's it, moles per litre. And in grams per litre. So now what I've got to do is I've got to go from moles per litre down to grams per litre. And at this stage, everyone knows how to do that, because we've got to multiply by the mass of sodium carbonate. Now, Na2, that's 23 plus 23, carbon is 12, and 3 oxygens is 48. So that gives me 106 grams per litre. Okay. Or sorry, grams I should say is the molar mass. So you multiply that by your 0.0432, and I end up getting 4.5792. Look, 4.58 will do fine at this stage. So I got 4.58 grams per litre. Now, that's that part done, moles per litre. My moles per litre was 0.0432, and then I want to turn it into grams per litre. So we multiply the 0.0432 by the mass of sodium carbonate, just put it in there. That's the mass of Na₂CO₃, and that gives me 4.58 grams per litre. Okay, but go back up here. How much crystals did I put into a litre? I put in 10 grams. Now, what does the titration say? The titration says that in those 10 grams, there was only 4.58 grams of sodium carbonate. So in the original 10 grams per litre, we noticed that there was only 4.58 grams of the sodium carbonate, which means that the rest of the mass must have been the water of crystallization. So 10 minus that gives me 5.42 grams of water. So now what I have is I have a ratio of mass between the sodium carbonate and the water in the original 10 grams. Okay, now you're probably saying, well, we didn't use 10 grams. But hold on a sec. No, we put 2.5 into 250. But for chemists, 2.5 and 250 is the same as 10 grams in a litre. And the reason why I have to use a litre is because it's a standard volume. Then down here, my titration said that there was only 0.0432 moles of active ingredient sodium carbonate in a litre, which I turned into grams per litre, and the titration tells me that in those 10 grams, there's only 4.58 grams of the active sodium carbonate, which means that the rest must be water. Now, this brings me back to one of the earlier stoichiometric calculations we had called empirical formula. You're not allowed to compare substances through mass alone, okay? Because the molecules are of different sizes. So what you have to do with both of these masses is take into consideration their molar mass and divide both of them by their own molar mass. Now, we've already said that that's 106, and water is 16 and 2 is 18. So 4.58 divided by 106, and that gives me 0.043. And then the 5.42 divided by 18, that gives me 0.301. Still doesn't look like a ratio. A ratio is the simplest whole number relationship. So now we take the smallest number and we divide it into everything down here. So that's obviously going to go into itself once. And 0.301 divided by 0.043 will come out as 7. And it's 7 exactly on your calculator. Now, what does that mean? For every 1 sodium carbonate I have, it will be surrounded by 7 waters. Now go back up here. See that? For every 1 sodium carbonate I have, it'll be surrounded with 7 waters. So that means that I've got Na2 Na₂CO₃.7H₂O. The X is 7. Okay. And what else do they ask me to do? The percentage of water in the crystals. Well, that's fairly okay. How many grams of crystals did I put into a litre? 10. Out of that 10 grams, how much was water? 5.42. So therefore, we change that into a percentage by multiplying it by 100, which simply means you're going to multiply 5.42 by 10, and I end up seeing that there is 54.2% water in these crystals. Okay, now you've got to do exactly the same thing with your values. So you have your table, you've completed your titration, you've got your table filled in. That's how you follow the calculations. And what I do want you to have at the end of the day is the concentration of the sodium carbonate in moles per litre, the concentration of sodium carbonate in grams per litre, the breakdown of how many grams are present in the original crystals belonging to Na₂CO₃ and water. So break up the mass between those two. Then divide the respective masses by the molar mass of each substance, work out the ratio between the two, and finally give me back the percentage of water that is present in those crystals.